All right, so what I want to talk about is just what a logarithm is and give you some sort of intuition for what's going on. And so I'll do that just by making a table here. And we'll start with, I think log base 10 is probably the most familiar one. So let's see, how do I get the base on there? I think I can go log base 10. Oh, I see. This is in the way. There we go. All right, so I need to get log. It's got a special function spot. Where are you? There you are. Okay, so log base 10 of x. Let's get this other log out of the way. There we go. And I actually don't, you can look at the graph. Sure, the graph's there, but I actually would rather look at this like a table. A couple things I want you to notice in this table. It doesn't work for negative numbers and for zero. It only works for positive numbers. And if I start looking at those positive numbers, let's see, how do I make it extend? There we go. So what I want you to notice is, as I'm going through this table, the y values increase very slowly. See how I'm already up to x equals 90 and I still haven't even made it to y equals 2. This is a graph that's always growing. Every y value is bigger than the previous y value. It's just not growing very fast. In fact, it was at 1 comma 0 and it took 10 steps to get to a height of 1. And then check out, if I go another 10 steps, it's not at 2, it's at 1.3. It takes me a lot of steps to get even higher than 1. Maybe you can predict when I'm going to land exactly on 2. I'm getting pretty close to it. And I land exactly on 2 when I'm at x equals 100. So what I want to do is write down a couple of the values here. Log base 10 of 1 is 0. Log base 10 of 10 is 1. Log base 10 of 100 is 2. Remember, all that I'm saying is that I've got the point 1 comma 0. All the way over here, I've got the point 10 comma 1. And way the heck off the screen, I've got the point 100 comma 2. Now, why do I have those points on the graph? The reason I have each of those points on the graph is because a logarithm is just a rearranged exponential equation. So take each of those three equations I wrote and switch them around to be an exponential problem. This is the same as stating 10 to the 0 is 1, 10 to the 1 is 10, and 10 to the 2 is 100. The logarithm is nothing to be scared of. It's just an exponential problem where you've switched what x and y are doing. Normally, when we're looking at exponentials, and up until this point in this unit, we've looked at problems like 10 raised to the x. Those have grown very quickly. Every one step we move to the right, we get 10 times as tall. Now we're switching that around. So instead of it being for one step, you increase 10 times, now it's you have to increase 10 times horizontally to go even just one step higher vertically. It's an inverse function. So every point on the exponential equation, y equals 10 to the x, has a buddy point on the logarithm equation. So for example, I chose 3 different points to point out on my red graph. Those 3 points have buddies on my black graph. 0, comma 1. Up here will be 1, comma 10, because 10 to the first is 10. Way the heck up there is going to be 100, comma 2. So a logarithm is just a rearranged exponential equation. Let's look at just a couple other examples. Oh, one other thing I guess I should point out. This is special just for log base 10, Don't overgeneralize this idea. This is just for log base 10. And the reason this is true for log base 10 is because we write our numbers as decimals. The word decimal means base of 10. If I look at a number like log base 10 of 1,000, the number is going to be 3. And you should notice a pattern going on, that the answer is the number of zeros on the input. See? The number 1 has no zeros. The number 10 has 1 0. The number 100 has 2 zeros. So now you should be able to answer any question that is log base 10 of any number of zeros. I don't even know how many I wrote down. But what I can do is just count them. 3, 6, 9, 10 zeros. So log base 10 of that number is 10. I guess, is that 10 billion or something like that? So that is one way you can use log base 10. And you can use that same idea that the number of zeros is related to the logarithm to make estimates about other numbers. Like, for example, log base 10 of 2,500. I know it is bigger than the answer for 1,000. If I did log base 10 of 1,000, I'd get 3. Well, 2,500 is bigger than 3, but 2,500 is bigger than 1,000, so my log has to be bigger than 3. But 2,500 is smaller than 10,000, so it's smaller than 4. So what I'm doing is I'm looking at the two powers of 10 that are on either side of 2,500. You have 1,000 is smaller than 2,500, which is smaller than 10,000. And so I have 3 zeros here versus 4 zeros there. And that's how I got this statement down here. Now, everything I just said in the last minute about the number of zeros, that's special for log base 10. What I'm going to show you now is another example that's not log base 10, just to make sure you get the general idea. Let's look at log base 2, everybody's other favorite logarithm. Come on, work with me. There we go. All right. Boop. Deleted. There's probably a faster way to do that. That's fine. All right, let's look at y equals, and we're going to do log base 2. Log base 2 of x. You can see a curve right there. I want you to compare that to the log base 10 of x. Actually, let's pop it back. Let's pop log base 10 of x back up there just to compare. What's different about the two of them? Why is the purple graph steeper than the red graph? Let's turn this into a table so we can look at our values. Notice again that we only have answers when x is a positive number. When x is 0 or when x is a negative, we have this undefined error. Now notice what's happening. I'm creating a table of values. Try to pay attention to when I get whole number answers. Notice that the y values are always increasing. Just like with log base 10, the log function is an always increasing function. That's probably good enough. Think about what numbers gave me whole number answers. 64 gave me 6, 32 gave me 5, 16 gave me 4, 8 gives me 3, etc., etc. What we have are log base 2 of 1 is 0, log base 2 of 2 is 1, log base 2 of 4 is 2, log base 2 of 8 is 3, etc. What I want you to notice is that every single one of these is an exponential equation that's been rearranged. I could rearrange each of these to be an exponential equation that is also true. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, etc., etc. What is a logarithm? A logarithm is a rearranged exponential equation. It's the inverse of an exponential equation. Oops, I made a mistake. I was going too fast. This shouldn't be 32. Should have been 64. Okay, just to have a little bit of comparison, and then we'll call it good on this video. If I do y equals 2 raised to the x, you can see that it is a perfect mirror of the other curve. It takes, for the exponential, one step to the right is 2 times taller. For the logarithmic, 2 times further to the right is 1 step further. I switched the horizontal and the vertical because we're just rearranging. So please let me know what I can do to help, but that's the basics of what a logarithm is.